Okay, so rational equations and inequalities. The rational equations we learned back in Math 3, so we're going to do a quick review how to solve rational equations. Starting with this first problem, we'll walk through the steps. You always want to factor your denominators if they're not factored, and then figure out your least common denominator and also what values of the variable would make the equation undefined. In other words, what values would make the denominator set equal to 0. So looking at this one, it's pretty simple. Our LCD would only be w minus 1 because it's the only factor we have in the denominator. And since we have that in the denominator, we know that w cannot equal positive 1. So what we're going to do is we're going to multiply the entire equation by the LCD so that we can reduce out those denominators. Some students will wrap their entire equation and they just know that they're distributing that w minus 1 to each term. Some students find it to be easier to write it beside each term so that they can actually cross it out where it needs to be. So we're multiplying each part of this by w minus 1. So in the first one, the w minus 1's reduce, and we are left with just w. In the next one, nothing reduces, so we have w times w minus 1. And then in the last part, the w minus 1 reduces, so we're left with equals 4w minus 3. At this point, we need to distribute and combine like terms and see what type of equation we are working with. So we have w plus, when we distribute right here, that gives us w squared minus w equals 4w minus 3. When we combine like terms, the w and negative w on the left side cancel. And so we are left with w squared is equal to 4w minus 3. At this point, it appears we have a quadratic equation, so we want to set that equal to 0. So I'm going to leave that w squared positive and make it easier to factor, or use a quadratic technique. So we would subtract the 4w, the 3 over to set it equal to 0. We then need to use a quadratic technique such as factoring or quadratic formula or completing the square. In this case, this one is factorable. We'd have w minus 3 and w minus 1. And when we set those equal to 0 and solve, we have w is equal to 3 and w is equal to 1. However, because 1 is a restriction, this is an extraneous solution. W cannot equal 1 because that would make the denominator equal to 0. And that's what an extraneous solution is. It's where you worked the equation out perfectly fine. It's just that one of your answers does not work. So in this case, we only have one answer, which is 3. So in this case, our only answer is 3. All right, looking at the next problem, the first thing we want to do is go through and factor out our denominators. So our first one's good to go. We've got y plus 2. The next one says 2 minus y, so I'm going to hold off on that for a second. But when we get to that third denominator, y squared minus 4, we recognize that's a difference of squares, so that's really y plus 2, y minus 2. Well, here's the thing. If I look at it the way it is right now, we actually have 3 factors that would have to be in our LCD. We'd have to have y plus 2, y minus 2, and 2 minus y. However, if you were to factor a negative 1 out of this 2 minus y, it would make it into y minus 2. So a quick way we can do that is we can reverse this and make this y minus 2 by factoring out that negative 1. And since we're actually subtracting this fraction, all we got to do to fix that is make that plus. So pretty much what it's like is you distributed the negative through that. You made that negative 2 plus y, which is the same thing as y minus 2. Or you can think about it as factoring the negative 1 out, and then a negative minus a negative is positive. So I'm going to rewrite this real quick. Okay, so from here, we want to state our restrictions. If we are to get negative 2 or positive 2 as an answer, those would be extraneous solutions. We want to make sure we always check those restrictions. Same thing as what our vertical asymptotes are. And now our LCD is going to be much simpler. We're going to have y plus 2 and y minus 2. So if we multiply every term by y plus 2, y minus 2, we'll be able to take out those denominators and work with just the numerator. Again, if you need to write it beside every term so that you can watch it cross out, that's fine, or just wrap the whole thing and distribute it through. Okay, so in our first fraction, that y plus 2 reduces, so we're left with 2 times y minus 2. For the next one, we have plus. That y minus 2 reduces, so we are left with y times y plus 2. And in the last one, everything reduces. The y plus 2 with the y plus 2, the y minus 2 with the y minus 2. So we are just left with that numerator of y squared plus 4. All right, so we have to distribute and combine like terms. So we have 2y minus 4 plus y squared plus 2y is equal to y squared plus 4. So when we combine like terms, that gives us y squared plus 4y minus 4 is equal to y squared plus 4. It seems to be quadratic. However, when I subtract y squared from each side, they cancel on both sides. So it's actually just a linear equation. So I'm going to add 4 to the opposite side. So that leaves us with 4y is equal to 8. And when we divide each side by 4, we get y is equal to 2. But then we need to make sure we check our restrictions, and we can see that one of our restrictions is 2. So since 2 cannot be an answer, in this case, our actual solution is going to be no solution. Okay, so for the next two, I want y'all to try them, but something I want to give you a little hint about that students really mess up with is both of these have subtraction in them. And the last one did too, but we were able to take care of the subtraction by rewriting that factor and making it plus. But when that does not work out that way, the best advice I could ever give you is go ahead and make that subtraction into addition and put the negative with the numerator of the following term. Where in this last problem, what I did was I put the negative with the denominator of that following term to take care of that. The reason why I say that is a lot of times students won't distribute the negative through and they get the wrong answer. And I would do the same thing with the next problem. I would make that plus and then make that z negative and make that 6 negative. All right, pause the video, try number 3, and then start the video back. Okay, so for this one, we have a least common denominator of n plus 3 and n minus 3. We also know that n cannot equal negative 3 or positive 3. So we multiply each term by the LCD. In the first term, everything reduces, so we're just left with 4n squared. The next one, the n plus 3 reduces, so we have negative 2n times n minus 3. And the last one, the n minus 3 reduces, so we have 3 times n plus 3. We then distribute, and when we do that, then we need to combine like terms. At this point, we subtract the 3n over from the 6n to get positive 3n, subtract the 9 over. When we factor, we get the factors 2n minus 3 and n plus 3, so we get solutions 3/2 and negative 3. But again, negative 3 is an extraneous solution, so we know we can't have that as our answer, so our only answer is 3/2. Okay, so this one requires quite a bit of little algebra in there. Our restrictions are 2 and negative 1, and our LCD is z minus 2 and z plus 1. If your handwriting is really messy and your z's get confused with 2's, just rewrite this problem with an x instead of a z. So when we work this out, again, I make sure I made that z and that 6 in that second term negative so that when I FOIL this out, all my signs work out. If not, you have to put parentheses around that and then distribute the negative through, and students tend to mess that up. Once we FOIL and distribute on each side, we combine like terms. We end up with negative z squared plus 16 equals z squared minus 1z minus 2. Move everything to one side, and we get down to a trinomial. In this case, this trinomial is not factorable, so it's a little bit simpler to use quadratic formula. Pop into our quadratic formula, and we end up with 1 plus or minus the square root of 145 all over 4. And since 145 is 29 times 5, we cannot simplify it, and that's our answer, and it does not have an extraneous solution in this case. Okay, so for the new part, rational inequalities. All right, so step 1 is going to be just like a polynomial inequality. You have to get everything on one side, set equal to 0. Step 2, we have to simplify this rational expression. We have to make it one fraction. And so in order to do that, we're going to have to use fraction rules like getting common denominators and those type of things. So if we look at this first one, we can see that our LCD for this problem would be x minus 2x plus 1 because it's already set equal to 0. So what we have to do is multiply each fraction by what it's missing. All right, so then once you multiply by what each fraction is missing, we're going to do our algebra and clean this up. So right here in the numerator, we're going to have 4 times x, 4 times 1, so that's going to give us 4x plus 4. And then on the next one, we'll have 2x minus 4, so plus 2x minus 4. We want to make this all one fraction over our LCD. Sometimes I just write LCD, so I don't have to keep writing it over and over again. When we combine our like terms, those 4's end up canceling out in the numerator, so we end up with just 6x over x minus 2, x plus 1. So once we get to this step, what we're trying to do is we're trying to figure out what would make this expression greater than 0. So in other words, if we were to look at this graph of this rational function, when is it positive? So to do that, we're going to set each one of these factors equal to 0 so that we can get the actual zeros of each factor. All right, so once we find the zeros, we're going to draw our number line just like we do with our polynomial inequalities, and we're going to make sure we put those zeros on our number line in the correct order. And I'm not going to have the spacing perfectly. I just want to make sure they're in the correct order and there's some space between each one. All right, in this case, it wants to know when it's greater than 0. But folks, if it had said greater than or equal to, you have to remember that the values in the denominators are not the zeros. They're actually where the vertical asymptotes are. So even if this was equal to, at those zeros, the ones that would represent the vertical asymptotes, and I'm going to put that right here, these would represent the vertical asymptote. This would represent the vertical asymptote. This would end up being the x-intercept. But those vertical asymptotes would actually always be open holes because that's where the function's undefined. In this case, though, they're all going to be open holes due to the fact that they it's only asking for where it's greater than 0. All right, once you get your open holes in there, we're then going to separate this with little dashes so we can look at what is going to be the sign in each interval. Now, the easiest way to do this is just to substitute values into these factors and decide whether it would make that factor positive or negative. So, for example, if I substitute a number less than -1, so let's just say -2, into 6x, it would make it negative. If I substitute -2 into x minus 2, that would be also negative. And if I substitute -2 into x plus 1, that would be -1, which is also negative. So if I do a negative divided by a negative times a negative, that's a negative divided by a positive, which is ultimately negative. So this section's negative. Then I'm going to do the same thing in the middle. So what if I substituted -1/2? The numerator would still be negative. For the x minus 2, it would also still be negative. But for x plus 1, if I do -1/2 plus 1, that becomes +1/2, so it becomes positive. So that's a negative divided by a negative, which would ultimately make this section positive. So now I'm going to substitute a number between 0 and 2. So let's say I substituted 1. 6 times 1 is 6, so that is positive. 1 minus 2 is negative, so that is negative. And then 1 plus 1 would be positive, so that's positive. What I'm doing is I'm substituting a number from each section into the 6x, the x minus 2, and the x plus 1. I don't really even care what the number is. I'm just trying to figure out would it give me a positive value or a negative value. So a positive divided by a negative is going to make this section negative. And then if we do the same thing for the last section, we end up with positive divided by positive times a positive, so this section's positive. Since we want to know when is this expression greater than 0, we are looking for positive values. So any section that was positive, that's where we're going to shade. So we're going to end up shading between -1 and 0, and then from 2 on to infinity. And we always write our answer in interval notation. So our final answer for this problem is going to be from -1 to 0 in union with 2 to infinity. And I find that's a lot easier to do the sign test in this case versus, or test values versus having to do it graphically, because these aren't always the easiest functions to graph. All right, let's try the next one. So this one you may think, oh yay, this is awesome, we're already in factored form. but it's not because it's not set equal to 0. So the first step is we have to subtract that 6 over, and we have to get a least common denominator for both of them. We subtract that 6 over, since that's just 6 over 1, the least common denominator in this case is going to be that x minus 3x plus 1. So we have to multiply the numerator and the denominator with that 6 by x minus 3x plus 1 so that we can get a common denominator of x minus 3x plus 1. And then that makes this whole thing less than or equal to 0. Well, now we've got to clean this up. And y'all, to make this simple, I'm just going to keep writing LCD under each one, so I don't have to write x minus 3x plus 1 a million times. What we need to do is clean up this numerator. So we're going to have to FOIL the x plus 2 times 2x minus 3, and also the x minus 3 times x plus 1, and then distribute that 6 in. So if we FOIL this first part, that's going to give us 2x squared. 4x and negative 3x is 1x minus 6. And then I'm going to put minus 6 with a bracket, and then I've got to FOIL that x minus 3x plus 1, so that's going to give us x squared minus 2x minus 3. Now I still have to distribute that negative 6 to that trinomial, so that's going to give us 2x squared plus 1x minus 6 minus 6x squared plus 12x plus 18 all over our LCD. So then when we combine like terms, we end up with negative 4x squared plus 13x plus 12 all over our LCD, which I'm going to now put back in here, is x minus 3x plus 1. And we know all of this is less than or equal to 0. I didn't carry that down, but I should have right here. All right. Once we clean this fraction up, we have to factor it so that it makes it easy to test all those values. It's going to be a whole lot easier if we can just substitute it into the different factors. Well, the problem is I can't stand how that numerator starts with a negative. So in order to get rid of that negative x squared, I'm going to multiply this whole inequality by negative 1. And what that's going to do is it's going to change all the sides of my numerator. So it's going to make that positive 4x squared minus 13x minus 12. My denominator will not change. It'll stay just like it is, over x minus 3x plus 1. But because I'm multiplying this whole baby by a negative 1, remember, when you do that with an inequality, it also switches the inequality symbol. So it's going to make this greater than or equal to 0. And then that's going to make that numerator a whole lot easier to factor. And if we factor that numerator, we get 4x plus 3 times x minus 4 all over x minus 3, x plus 1 is greater than or equal to 0. Okay, so from our knowledge of graphing rational functions, the zeros, or the x-intercepts for this rational function, are at negative 3/4 and at positive 4. But from the denominator, the vertical asymptotes, or the undefined values, because remember, the vertical asymptotes are what makes that function undefined, or if you think about the equations, they're the same things as the restrictions, are positive 3 and negative 1. And then we're just setting those factors equal to 0 to get those. So we need to put these numbers in order on our number line. Well, this one's going to be a big one. So from least to greatest, we have negative 1, and then we have negative 3/4, and then we've got 3 and 4. Now here's the difference on this one. Looking at where we've cleaned this all the way up right here, we want to know what values are going to make this rational function greater than or equal to 0. But we're not going to put closed holes at all of these numbers because the vertical asymptotes are where the function's undefined. So where the zeros are, we can put closed holes, but where the vertical asymptotes are, we need to put open holes since that part is undefined. So at negative 1, we're going to have an open hole. At negative 3/4, a closed hole. At 3, an open hole. And at 4, a closed hole. That creates 5 sections, and now we have to pick a number from each section, substitute it into each of these factors, and decide would it make that factor negative or positive. I really don't care what the number is. We just need to know if it's negative or positive to figure out whether the whole quotient comes out to be greater than 0 or not. So for this first one, let's say we substitute -2. If we substitute a -2, the 4x plus 3 would be negative. The x minus 4 would be negative. The x minus 3 would be negative, and the x plus 1 would also be negative. So if we multiply and divide 4 negatives, that section will be positive. If we pick a number between -1 and -3/4, let's just say it's -0.8. It is going to make that 4x plus 3 negative. It's going to make that x minus 4 negative. It's going to make the x minus 3 negative, but it's going to make that x plus 1. If I put -0.8 plus 1, it's going to be positive. So an odd number of negatives is going to make this section negative. All right, the easiest number in the next section to substitute would be 0. So if we substitute 0 into 4x plus 3, it's going to be positive. The x minus 4 is going to be negative. And the x minus 3 is going to be negative, and into the x plus 1 is going to be positive. So an even number of negatives is going to make this section positive. If we substitute a number between 3 and 4, let's say 3.5, it's going to make the 4x plus 3 positive. It's going to make the x minus 4 negative. It's going to make the x minus 3 positive, and the x plus 1 positive. You can see once they switch from negative to positive, they don't change over. And then the last section, they'd all be positive. So this second to the last section, we have an odd number of negatives, so that section's negative, and then the very last section is all positive, so that section's positive. In this case, we wanted to know, once we clean this all up and flip that symbol, when is this greater than or equal to 0? So we are looking for positive values, or where it's equal to 0, which we already got the zeros on there. So we're going to shade everywhere it was positive. So that is from -infinity up to -1, and then from between -3/4 and 3, and then from 4 to infinity. And we always write our answers in interval notation. So that's going to be from -infinity to -1 with a parenthesis in union with bracket -3/4 to 3 with a parenthesis in union with bracket 4 to infinity. And that's a big one. Not all of them are going to be that big. So you kind of have like some smaller ones and then maybe one big one in your practice. So we have 4 equations for practice and 4 inequalities for practice.